All right, hello everybody. This is Dr. Yuzo, and this is ECE 318 Electronic Circuit 1. And can everybody hear me well?
Yep.
Okay, thank you, Shane. And let's start our lecture today. This is our ninth lecture, and as you know, 1 week ahead of the midterm one, so we're gonna do a review for midterm one today. And besides of that, we're gonna learn how to analyze the Clipper circuit, okay, and a little bit the clamper circuit as well, since we have done the lab today hours ago. And before everything, I wanna mention a little bit the canvas, the canvas thing. First of all, everybody, please remember, if you want to track the progress, find out the upcoming deadline and upcoming assignments, something you need to do about this course, remember, don't go to the calendar. The calendar's organization is actually not as organized and not as clear as the modules. So don't go to the calendar here, and also don't relying on the manuals here either. Just go to the modules. Okay, remember how to browse, how to find the information about the course. Okay, everything. Just go to the modules, and everything is organized into the modules. Okay, and under the manual of assignments, you know what you need to do and when is the due time. Everything is listed there, very clear. So it's not surprised that you see the first homework 2 is due by October 13th. And also we have a test run exam. Appreciate 4 of you guys have already done those. And also I changed the due time because I noticed some of students still willing to do it. I just missed the deadline, so I reopened it. Okay, I have reopened it, and the due date of this test run exam is October 5th. Okay, next Monday. Therefore, the next Tuesday lecture we can discuss if any problem, any concerns raised up. Okay. Once again, test run exam due date is extended to next Monday. Okay, and also here you can not surprised that we are seeing the exam 1 and upload exam 1 answer file, okay, 2 place. So if you want to find something, if you know what you need to do, where to go, well, calendar is helpful, but not the best place. Once again, the best place is and always is the modules, because I have organized the class into such format. Everything is placed, stacked in the modules. All right. This organization, if you can realize that, is actually even better than the face-to-face course organization. Okay. So using the modules. Okay, use the modules all the time. I use the modules all the time. Okay. So this is a little bit the canvas. And regarding those 4 students who have done this, most of the questions are trivial. And what favorite show? 2 students saying no time for TV shows. Well, as poor as I am, and well, all of them are very quite uniform answer. I don't like it. I don't like the online teaching and learning for engineering courses. Well, yeah. And also here, this is a question, not non-trivial question. Okay, I really want to know where student at about this, because Monism is required for our not only labs but also the final project. So we need to have a solution for it. We really need a solution for it. And among these 4 students, only 1 student saying, no, I haven't yet think about it. But think he has thought about it quite a bit. So he's a thoughtful student. So I'm not quite worrying about it. And the rest of you guys seems okay. But once again, as I mentioned today in the lab, according to my announcement, be careful that don't use it until kind of approaching to the Thanksgiving. Okay, this is the reality for at least this semester. And maybe next semester, another ECE 318 or 358 classes will get a chance to use the free license of Multisim from school. But this semester seems not. Next semester is maybe. All right, this is the Canvas thing. Now I would like to first of all review the exam. So what exams we have? What problem are going to be covered? So first one is multiple choice. Okay. Multiple choice, I'm thinking either 10 questions with 1.5 points per question, or 15 questions, but 1 point per question. Is that clear? So it might be either way, okay? Either way. So either or, okay? Either this or that. Okay, this is multiple choice. Many students ever ask me how to prepare this multiple choice. My answer is this is actually assessing students really the real engagement in the class. Okay, so and luckily we have the recorded lecture videos. So if you want to review the multiple choice questions, I can only guarantee you that are absolutely something we have ever discussed in the lecture. Nothing is something you never heard of from this class. Okay, I can guarantee this. However, which part? Well, of course, from the Gantt chart, we can tell it's covering the module 0, 1, and 2. Right? Module 0, 1, and 2. Definitely won't cover anything about module 3 or above. That doesn't make any sense. Okay, module 0, 1, and 2. These are all I can provide. Any questions? Any concerns about multiple choice? Oh, good. All right. So this is the first one. Obviously, the multiple choice is inside of the exam one. I mean, you're gonna do kind of online Canvas quiz. You just click the correct option. Yeah. And then you have problem 2, 3, and 4. Okay, 2, 3, and 4. All of those 3 are handwritten works. Handwritten works. What do you mean by handwritten works? They're just nothing but circuit analysis. And what are they? Okay, this is the key you wanna understand very well. So we're gonna have one calculation problem for diode circuit analysis. Here I'm talking about this is a DC analysis plus AC small signal analysis. Be very careful. Okay, what does it mean? It means given what? You're seeing a DC source plus an AC source. And then compared to the DC source, your AC source has very small or say tiny magnitude. Therefore, it is called small signal, right? And therefore, you are applying the small signal model. That's the key. Who remember what is the signal model of the diode? Anyone knows? What is the small signal model for the diode? Anyone still remember?
Open circuit.
No. Open
The
circuit.
resistance.
Very
Yeah.
good. Very good. Very good. And what we call it, RD, right? RD. Okay. And here by the model, I mean the on model, okay? Because it is, if it is off, then of course it's open circuit. Okay. Then what is DC model? DC model is what? Everyone should know this, right? Everyone.
It's source.
Exactly. With voltage off, cutting voltage. So this is the model. So this is the one circuit. And we have examples in the PowerPoint slides. And also we have one homework, homework 0, actually. Homework 0, we are dealing with, not dealing with diode. However, we are dealing with a source, right? Source, which is given like something like this, right? Remember, 5 plus 12 milli sine omega t, right? Remember that source? This means nothing but one DC and one AC. However, AC's magnitude, you see, way smaller than the DC. So small signal model, right? Being clear, this is one of the calculation problem. And when you do it, you really need to, first of all, correctly identify this problem. Okay, this is a DC analysis plus a small signal analysis. You need to be very clear, correctly identify that circuit, and the thinking of the corresponding knowledge and the examples we have done before. This is one calculation problem. And we're going to have another calculation problem is the diode rectifier circuit analysis. What does it mean diode rectifier circuit analysis? Instead of DC plus AC source, what source this time is given? Anyone remember?
Is that the AC source?
Exactly, only AC source, only AC source. You're not having any DC source, okay? However, this AC source is what? Large signal. Whose value is what? Anyone remember? What is the AC large signal model for diode? Anyone remember? What is the AC large signal?
Same as DC model.
Exactly. Kevin is right. Okay. It's same as the DC model. Here we go. Okay. Very good. And the we have a notes you should check. I summarize 3 different models in one page, right? On one page. You should have this note. And even the AC source. Well, of course, we learned 2 types, right? One is what, half wave. Another is full wave. Right? I'm thinking, but just try this option rather than the second one. Okay, this is my plan. And hopefully I won't change. I'm kidding. I'm not planning to change. Half wave. By the way, what does it mean by half wave? So in the circuit, how many diodes are you going to see?
Just one.
Exactly. Good. Very good. Very good. How many in full wave? Anyone remember?
4.
4. Very good. Very good. 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 Good.
There's a question in the chat as well from Daniel.
Yep. Yeah, we're all good. 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 I see Kevin and two for my questions are very good as well. Well, I saw Daniel's question and I prefer to answer that at the end. It's and let's talk about the knowledge-wise first, and then we can talk about the policy. This is the second one. And third calculation problem is a Clipper diode Clipper circuit. Clipper circuit analysis. According to the experience, this is the most difficult one. Okay, this is the most difficult one. Today we're gonna learn a couple of Clipper circuit analysis. According to what happened in the past, students struggle with it. So let's see. Okay, let's see. The logic is it seems not quite easy to follow, but maybe you see. Okay. Clipper circuit. I call it what? I call it lecture 9, maybe as well as 10, which will be on next Tuesday. Because today, if we can't finish all of them, okay, next Tuesday, continue, right? So just remember to learn the things from today and the next lecture, maybe. Okay. So by talking about them, the reason, look at this review, okay? Let me talk about my style here. I'm trying to make you be very clear that what kind of a problem you are going to see in the exam, before the exam. So as long as you learn and follow and you understand what I'm talking about here, you should not have any surprise in the exam. Okay, my exams have no surprise. Okay, except now when we talk about here, you don't understand what I'm talking about. I'm talking about here, you don't understand what I'm talking about. Well, of course, you don't understand what I'm talking about here for sure, because I haven't yet talked. Okay, so when I talk about these two problems, you should be able to immediately come up with, okay, that's which lecture slides and which example exactly, specific examples I should follow. Okay, you have a target to prepare rather than in the middle of nowhere. Okay, this is my style for exam. And in the exam, I probably give you you never seen before, but still follow the same procedure, follow same idea. The same procedure we used in the in-class examples. No surprise, okay, no surprise. If you in the exam feeling like you're doing something you never done before, 9 out of 10 that you are doing something wrong. Did I make myself clear? No surprise. Okay, no surprise. Remember this. If you really feeling in the exam you're doing something you never done before, it's brand new. Very, very, very likely you're doing something wrong. That's abnormal. Remember this. Circuit different, of course, different. However, the procedure, the idea should be same. Okay, should be something you have done before. Well, except you never attend the lecture, you never watch the recorded lecture, you didn't do anything in this course. Of course, everything gonna be new. However, I'm not expecting that from anyone in this class. Okay. All right, going back to the Daniel's question. So is my partial credit policy the same as normal? First of all, of course, what do you mean by normal? How you define this normal? I speak normal for your classes. I'm a little bit surprised that you still remember my partial credit policy back in 235. But to rest of you, let me explain my grading here. First of all, my grading way is like this. Okay, I have 3 different markers. 3 different marks. Okay, this means what? You're receiving credit, right? You're right. Point. This means what? Easy. Lose point. Because it is wrong. However, I have a third. This one. This one means what? Yesterday, I asked the same question to another of my class, and one of the students answered, I really don't like. I really don't like. He said, this means kind of right. Come on. In my class, in my exam grading, there's no kind of concept. Either right or wrong. Okay, remember this. There's no kind of right, kind of wrong. No, there's no blur region, and there's no gray region in between. Okay. This means what? This means this result is wrong. That step result is wrong. However, that step is correct. Your wrong result is due to the previous wrong remedial step result. Therefore, when you see this mark, you are not losing point. Instead, you're receiving point. Did I make myself clear here?
So that last one would be more of on a like the final answer to a question rather in the middle of
Correct. Well, it also depends on which step you have this, right? If your first step is wrong, of course, everything else is this. Does it make sense? Assuming if everything else is right. You know what I mean? Is that clear?
Yep.
Yeah. If you're just somewhere approaching to the end, you have a cross here. Your final answer, of course, wrong. However, your final step might be right. Therefore, you're not losing points once again. Okay. This is my partial credits policy. Okay. Other than this, I think, and also how I grade you guys, I think I need to clarify a little bit. How I grade you guys is like this. Okay, you guys have a multiple choice problem here. Of course, the online multiple choice problem do not need me to. You can understand. Okay, I just provide you a correct solution to the quiz. Automatically grade for me. I don't do anything here. To this 3, I need to step by step track your answers. Okay. There's no kind of right or kind of wrong concept. No, nothing like that. Okay. Not in my class. However, how I can grade you guys is like this. I'm grading problem 2 for everybody 9 times in this class, followed by grading problem 3 for everybody 9 times, followed by the grading of the very last problem, this guy, another 9 times, because we have 9 students. Okay, this is how I grade you. What does it mean? It means I basically don't know who I am grading for. So, for example, I know Kevin is a good student, Shane is a good student, and Well, without being aware that probably giving some biasing on them, no, I can't. Okay, no matter whom I grading. First of all, I don't know who you are. Okay, everyone is same to me. Okay, I'm grading the same problem for everybody in a row. Therefore, the similar mistake can lose same amount of point. Okay, there's no biasing or unfair treatment to anyone. Besides, I have a rubric. I have a rubric set up. Every step has a particular assigned amount of points. Okay, it's already preset rubric over there. Okay, if needed, I can show it up anytime after the exam. Of course, not before, not now. So this is how I grade you guys. Being fair is my first priority in grading. So other than that, I'm thinking oh yeah, another thing you need to be very careful. Also one of my styles. Equations are most important. Okay? Equations are most important because we are talking about analysis, right? So equations, most important ones. Those are pretty much indicating whether you are able to come up with analysis as a engineer. And based on those equations, you obviously go ahead to conduct the algebra to calculate the results, right? However, that procedure, I don't quite give giving a lot of points, giving a lot of credits for those works. Engineers are good at thinking, good at coming up with the solution, rather than conducting the math algebra. That's not engineer's job. That's not an engineer's, at least not the engineer's major job. Okay, so be careful how to manage your time, right? This matters for managing time. I mean, maybe you have plenty of time. You don't need to worry about anything. You're fine because the time to you is just too much, plenty. But if not, then you need to be careful. Okay, give your time to the engineering's job rather than algebra. Okay, so spend most of your time on making sure your equations are right. Okay, rather than the algebra. If your algebra is wrong, you come up with the wrong answer. Well, you're definitely gonna lose a little bit. That's for sure. Okay, that's for sure. The correct answer is 10. You end up with 100. Of course, you're going to lose some point, but very little compared to the equation. That's nothing. Okay. This is also I want to emphasize. Okay, how to manage time in case you don't have plenty. All right. Anything else about this midterm one? Any concerns regarding the coverage and the policy, etc., etc. Oh yeah, one last thing. I do have a curving policy. Okay, policy is like this: if the average is about 75% or equal to 75%, I won't do any curving. It is what it is. Okay, it's already all set. However, if the average is below 75%, I'm gonna curve it back to 75%. Therefore, I can guarantee each exam's average is equal or greater than 75%. Okay, this is my curving policy. By the way, anyone knows 75% in my class is what in terms of letter grade? Anyone knows?
B minus.
Here we go. Here we go. correct. Okay, so an average of each exam is at least B minus average. So this is another policy. Any other questions? Any concerns about my style? And because I do notice many of you guys the first time taking course from me, so I think it's beneficial to explain these things. In future class, you guys attend like a 360, 341, and some other electives, same policy, same idea.
You said we are allowed to have like an equation sheet.
Correct.
Right?
Equation sheet, please. Letter size paper, double size, if that makes any difference.
Yep, thank you.
Sure, no problem. No problem. Anything else? All right, if it's okay, then let's just move on to the Clipper circuit today. Now let's do some Clipper circuit and see how bad it is. All right. We begin with some slides here. Clipper circuit. Okay. If we just take a look at the circuit, is not very difficult. It's not complicated circuit at all, right? I mean, what you're seeing is one source, and the source is sinusoidal. Okay, a sinusoidal AC. Please remember this. Clipper circuit is the input is sinusoidal AC. Okay, sinusoidal large AC, not small signal AC. Yeah, large AC. Yeah, large AC. Okay. You probably want to take a notes. Clipper circuit means large AC as the source. Okay, large AC as the source, and therefore you can imagine the diode on model will be a power supply. Will be a power supply. Okay, with voltage of V gamma. Okay, and then it goes through a resistor, and then it goes through a diode in this polarity, and it goes through a battery, right? A small battery. VB means nothing but small battery. And try to find the output voltage here. The basic idea for circuit analysis actually is same as the diode rectifier. I mean, it makes sense because the Clipper circuit and the diode rectifier circuit, they're all under the roof of diode circuits, this module, isn't it? But it makes perfect sense. The analysis procedure, the basic idea, very bottom, no details yet, but the rough idea is same. What is it? What is the idea? Just the first find the range of input AC source, or say along the omega t axis, or diode on and off respectively. What I mean is, no matter what, you need to find what range, what is the range, or say time window, or say omega t position window for the diode to be on and off. Remember what we did previously? This is the input, right? What we did, we kind of find, okay, here the diode is on. Up to here, this diode is off, right? Remember what we did here? We need, no matter what, we need to find this range. Okay. Second, what we need to do, find the circuit when diode is on. And diode is off, respectively. Does it make sense? Okay, now I know this time window during this time, not time window, I'm sorry. Keep saying it's omega t position window. Because this is an omega t. It's not t, right? But it's not a big deal, okay? And during this window, the diode is on, okay. And then correspondingly, what is the circuit? Okay. Why we are looking for a circuit? Because based on the circuit, we can find what? The output equals to what? When diode is on and off, respectively. Does it make sense? Without the circuit at on or off, how can you find the output? It doesn't make any sense. Because when diode is on and off, they have different circuits, right? So before finding output voltage, you need to find the, or find whatever the problem I'm asking for. Okay, that's what I mean. Before finding it, you have to find the corresponding circuits, based on which you find out the voltage or maybe current or whatever the problem I'm asking for. Okay, this is the idea. Find the range, once again, range, circuit, and whatever the problem I'm asking for. Generally speaking, it's the output voltage, right? Like today, we are looking for the output voltage all the time as well in the lab, right? So basically, we are just, no matter what, we're just looking for these three things. Okay, keep this in mind, and this is a bottom line idea. Very rough, however, is universally valid. Okay. So with these being said, let's go ahead. Now let's go ahead to have details, to take care of the details. Take care of the details. By details, I mean this circuit. The circuit, how to find the V0? The detailed procedure for Clipper circuit analysis is like this. Generally speaking, we can, based on the KVL or KCL, come up with an equation from where we are deriving VD. What is VD? VD is nothing but the voltage across the diode. Because this voltage is determining forward or bias of the diode, right? Only this voltage can tell the diode is on or off. And then the tricky part is at the boundary condition. Boundary, what does it mean by boundary? Boundary between on and off. Between on and off state. The diode is not fully on yet, but it's trying to be turned on. So that at that boundary moment, we select that moment, because at different moment we might have different circuit. At the boundary, we are assuming the diode is not fully on yet, so we are assuming the diode current is 0. So basically means the diode, assuming at that moment is not on yet, is off. And then based on this boundary condition, we are trying to derive two states. One is on and the other is off. So based on VD is greater or equal than V gamma, or it's less than V gamma. One is meaning the diode is on, the other is off. From this, we are find out the range, circuit, and V naught. 3 things. Okay. Let's do it. Let's do it. How to do it? Let's do it. Do this. Let's do this. I'm placing this to here. Okay. According to this first, according to a KVL in the loop, what equation we can have? How about this equation? A single loop circuit, therefore, is fairly easy. Okay, it's fairly easy. Don't think too much. Don't overthinking it. Just inside of this loop, right? Does that make sense? Just inside of this loop. Right. Negative VI plus the voltage across the resistor plus the VD, then plus VB. VD and VB, and equals 0. Right? This is the KVL. From this KVL, be very careful. We are deriving VD. Once again, we are deriving VD. We are not deriving V naught yet. Okay, not yet. V naught is the last step. Now we are deriving VD, based on which we can tell the diode on or off. All right. So VD equals what? But from this equation, it's very easy. Just derive it, right? Equals VI minus IR minus VB. Very straightforward. Okay. Very straightforward. Third, what? Boundary means ID equals 0. ID equals 0 meaning what? This is a single loop circuit, so ID equals to what? ID equals to I, which is 0, 2. Okay. So at this boundary, what we have is VD just equals to VI minus VB. Right? By the way, what is VI? VI, as we said, is large AC signal, so it's just equals to magnitude VM, let's say VM sine omega t. Right? Perfect sinusoidal, and large signal. VM is big enough. It's big enough. It absolutely can exceed the V gamma, as well as VB. This is the VD equals this. So based on this VD, we start to do the fourth step. Your VD equals to VI minus VB. Okay, repeating it. Could have 2 scenarios, right? First one is what? Equal or greater than V gamma. Second is less than V gamma. Obviously, we understand this means the diode is on. This means diode is off. Very clear. Only 2 scenarios. Right? So VI minus VB greater or equal than V gamma means what? Means VI is greater than VB plus V gamma. Here, very careful. Okay, we are deriving VI. We are deriving VI. Or say, what is the relationship about VI to VB and V gamma? Okay. The students, generally speaking, hard to accept this. We're trying to derive Vi from this equation. Review C, Y is deriving Vi. From here, Vi is obviously here. VB plus V gamma. Make sense? Okay. Once again, derive Vi. Why we are doing this? Because this is nothing but the range we are looking for. Because this is nothing but range we are looking for. Review C. Okay. And in this range, what's the next? Circuit. Okay. The circuit. So when the diode is on, what the circuit should look like? Well, we go back to the given circuit. Okay. The circuit is just like this, right? This will be not. Does it make sense? You have, well, this is what? V what? V gamma. Second one is what? VB. This is R. This is VI. This is the diode is on, because this is here. This diode is on, and what is the circuit? Okay. Next, when diode is off, then what is the circuit? Open circuit. Diode is off means open circuit. Right. Extending my notes, I should do this. Extending my notes, but I'm going to extending from here. Also parallel two lines. Also two parallel two lines. What is the next? The last thing, which is V naught. Remember three things: range, circuits, and what? V naught. Remember the basic idea we just talk about? Range, circuit, V naught, right? Here, range, circuit, V naught. If these make sense, then obviously the next is when it is on, when the diode is on, what is the V naught? Anyone knows? The diode is on. What is the V naught? Anyone?
V gamma plus VB.
V gamma plus VB. Good. Then what is the V naught when the diode is off? Remember, when you looking for the V naught, what you are watching is the circuit. nothing else. Okay, it's a circuit. Now you have circuit, just to focus on the circuit rather than anything before it. Okay. In the circuit, what is V0?
It'd just be VI.
Excellent. Done. What I said. Range, circuit, V0. Done. Well, of course, the problem is not done yet. So what's left? You guys know what's left? Well, because by here, you're receiving like 80% or maybe 75% of the point. You still have a quarter amount of work to do. What is it? Anyone knows? Anyone aware? What next? Number 5. What to do?
Do you do the waveform graph?
Oh, very good, very good. Let's plot it. Plot it. Let's just plot it. How to plot this is not very straightforward according to what students have done before. Okay, so let's go over it together. So first of all, in the exam as well, okay, in the exam as well, this is provided already. You're not worrying about this. VI. These are given, okay. I'm not wasting your time to plot this. Okay. This is something given. Okay, this is something given. Okay, this is something given in exam as well. And what you need to do is plot the your output, your guided output. And also very important, you know the range for these two outputs respectively. You know the range, never forget that. So what you do here is this, right? Look at the range for the diode to be on. What is it? When VI, who is VI? VI is here, sinusoidal. When VI is greater or equal than VB plus V gamma. So first of all, VB plus V gamma is what? It's a constant. So your V gamma, which is sinusoidal, is comparing with what? With a constant with value of VB plus V gamma. Does this make sense, this idea? You just plot this constant into the graph. Okay, the black sinusoidal is comparing with the blue dashed line here. Does it make sense to you? Of course, VB, V gamma might be any value, right? Might be any value given in the exam, because in the exam, the values are specified. But here, we don't have to, right? So let's see what happened. This part means what? VI is less than VB plus V gamma. How about this part? VI is greater than VB plus V gamma. Does it make sense? And then what? This part means what? VI again less than VB plus V gamma. And then this part, VI is beyond the VB plus V gamma. Therefore, immediately you are able to come up with the range in the axis. Now this is why that is called range, because by VI relations with this guy, we are able to come up with the range. This range is what? Diode is on. Does it make sense? Because during this window, VI is beyond VB plus V gamma. When VB I is beyond VB plus V gamma, the diode is on. The result is V gamma plus VB. Therefore, during this range, how to plot V naught? V gamma plus VB. We just mentioned it's just this value. What can we do? Right? This range, diode is off. The next on will be here, right? So during here, the diode is what? Off 2. On and 2 at the next intersection. Does it make sense? One is on, we just mentioned, it's already constant. It's just a constant. VB plus V gamma. It's off. What is it? That is off. The output is just VI. How to plot VI? Copy VI. VI is here. So during this off, we copy. VI is here. Okay, VI is here. Give a little bit curve. That will be fair. This is off. Window. What do we do? Copy VI. Copy. Easiest thing to do, isn't it? Is copy. We really copy. And the negative peak here is just equals negative VM. Done. This is really done. Does it make some sense?
Yep, makes sense.
Good, good. Thank you. The procedure based on the students' performance seems not very easy. However, if you can follow here, it shouldn't be off by too far. Okay. Any questions? Right, if this is fine, then we move on to do, well, of course, this is just the result. This is the result from textbook. And how we get here, we just analyzed on the paper. Okay, this is the result. Exactly same idea for the second circuit. This time, let's do step by step, kind of on your own, maybe this time. Not completely on your own, but with my guidance. Let's together place it here once again, and let's do first step. Once again, the KVL inside of a loop. What is it? How about EI again plus BB plus IR minus VD. Zero. I'm making a mistake here. Can anyone find out what is the mistake here? Can anyone see this KVL is not quite right?
Your diode is reversed.
Well, that's actually exactly not the mistake I make. Be very careful, everybody. When you define a VD, you're defining the anode as positive, cathode as negative. In that way, you can say VD is greater or equal than the V gamma or less than V gamma to decide on or off, right? Because if you reverse the polarity when you define it, then, well, then the result can be completely different, right? You reverse the VD's polarity, then you need to say then VD is less or equal than the V gamma, the diode is on, right? So you to remember, don't mess that up. Anode, which is the bottom here, must be the positive. Does it make sense? Very critical, very, very critical. Okay, very, very critical. When you defining the anode as positive, cathode as negative. Okay. By the way, anode is represented by letter A. Cathode is represented by letter K. I don't know why, because cathode is beginning with letter C, right? But it's represented by letter K. Okay. Does it make sense what I said here? It's very important. Okay, very important. We need to define it in this way. Okay. Otherwise, the result, the conclusion on and off is opposite. So this is not the mistake, but a very good point. Any other one can see what's the mistake. It's a little bit tricky. It's here, actually. It's here. Why is that?
Because current is flowing the other way due to
Exactly.
the diode being flipped.
Exactly. Your current is flowing what? Counterclockwise, okay? Or zero. There's no way for the current to flow clockwise because of the diode. Does it make sense? So when you write a KVL, you gotta be careful. Even though this sign actually doesn't affect the result. Actually, it doesn't. However, when you write something, you need to be very careful. Okay, this is the first step, KVL. Second, we are doing what? According to your notes from previous example, we are trying to derive what? Anyone? VD, very good. 2 is right. Deriving VD. Right? These are not difficult. These are not difficult. Third step, a boundary, right? This is what we do. Boundary means ID is equal to 0. Now, ID equals 0, then ID just equals to I, and just is equal to 0. We are able to derive the VD now as equals to VB minus VI. VB minus VI. So far, everything is same as the previous example. So we follow same procedure. This is V. Next, it's time to derive the range, so-called range. So this VD, which is equal to VB minus VI, going to be two scenarios, only two scenarios. One is gamma or less than gamma. This means diode is on, this means diode is off, right? Very clear. What's next? Anyone? Deriving what? What's next? Find range, right? Which means deriving whom?
VI.
VI, here we go. VI. So basically, VB minus VI is greater or equal than V gamma. The VI means what? Less or equal than VB minus V gamma. Does it make sense? And to second off case, and then the other way around. This is what we call what? This is what?
Range.
Range. Here we go. One of the thing I'm looking for in the exam to grade, to give points. Does it make sense? In the lecture, I'm saying looking for range, circuit, and output. Well, I won't be surprised that in the exam I'm grading you guys in the same way, right? This is where I'm gonna give the credits. Give the credits. So next is what? After range is what? Circuit. The circuit is what? Output voltage, right? So give you guys 3 to 5 minutes to finish the circuits and output yourself. Go ahead. 3 to 5 minutes, circuits and output. All right, folks, let's see the circuit here. So when the diode is on, then the circuit it's just like this, right? I mean, input is over here, battery here, resistor here, diode is on, okay. You know, diode is off, if of course it's easier. Therefore, the corresponding V naught and V naught. First of all, the first one, this when the diode is on, what is the V naught? Anyone?
Negative VD.
Negative V what? Negative VD.
Gamma.
Correct.
Sorry.
Negative VD is correct technically, but negative V gamma. Okay, negative V gamma. Then V naught is what when the diode is off. What is it?
VI minus VB.
Good. Very good. Very good. Very good. Any questions regarding now the range, circuit, and output? Any questions regarding the? All right, if these make sense, then the next, go ahead. Translate all of these to a graph. Translate everything to the graph. Now you don't need the circuit, the original circuit anymore. Now you don't need it. You just need a range and output to plot. Go ahead. Give you guys another 3 to 5 minutes, and then we will see the solution. And then we call it a day. All right, let's see the solution here. According to the range and the V naught, as we said, so when Vi is less or equal than VB minus V gamma, well, VB minus V gamma is once again a constant. Okay, with specified value, you probably can understand this even better. But here is no matter what is a constant. So black Vi as compared with the, once again, the blue dashed line VB minus V gamma, right? Constant. We intersect with the Vi to create different position omega t windows, right? Does it make sense? Once again, it's all up to the intersections between the black and the blue. Obviously, in this range, the diode is what? On or off? In this range. Anyone?
That would be off.
Very good. Off. Why is off? Vi is beyond VB minus V gamma. It's greater than that. You go back to here. Vi greater than VB minus V gamma. It means what? It's off. Therefore, the corresponding output is what? Is what?
That same waveform just shifted down a bit.
Exactly. Vi minus VB. Vi minus VB. Now, Vi minus VB. Okay. Of course, before that, if you feel Vi minus VB is a little bit tricky to plot, because from here you can't tell very well how much you're going to shift down, right? You can begin with on window. Right? This window is on. So is this window. What is on? Because Vi is below the VB minus V gamma. Therefore, the V gamma, the diode is on here. Our corresponding output is negative V gamma. Negative V gamma is easy to plot. A constant negative V gamma here. Negative V gamma here. Right? Very easy. Right? It's on state. Off state means Vi minus VB. Vi minus VB. Vi minus VB. Vi shifted down by VB. Vi, this portion is like this, okay. It's not entire half cycle, positive half cycle. No, it's not. It's just a cap, the top here. And therefore, the peak value here, if you label as equals to what? The peak value. What is it?
Vi minus VB.
Vm minus VB. Okay, Vm is the peak value, okay, minus VB.
So Vm is just an alternate way of saying VPK.
Vm, you mean the peak value?
Yeah, that's just an
The
alternate
peak
form
value,
of
yes, it's gonna be given as well. Right? It's gonna be given as well. So in the exam, is become easier with specified numbers. With the symbols, of course, more abstract. Right? With specified numbers, it could become easier. Okay, done. Now it's done. Now it's done. Go back to the slides. It's just like this. Exactly same. Right? Exactly same. Well, of course, only that. Well, of course, we read it. Be careful. Okay? This line is zero. Okay? Not this dash line. Dash line is not zero. This solid line is zero. Okay? It's labeled as zero. Okay? Be careful. Negative V gamma. Well, obviously he is assuming the magnitude of the AC Vi is very big, so V gamma is neglected. Does it make sense? So V gamma compared to Vm is too small, so you can't see it very well. That's what it is doing, man. That's what it is doing. Okay, V gamma is too small. So this is What does it mean? Okay. And the third circuit in this Clipper circuit is nothing but the one we did in the lab today. Chop off the top and bottom. This is so you can try to do this. All right, I think I just stop here, and thank you for attending today's lecture. And leave you kind of a review, maybe review or have more Q&A on Tuesday. Yeah, Kevin, what's yours?
I just had to reload the conference. It kept kicking me out.
I noticed that, but you have recorded one, so no worry. All right, so thank you again, and talk to you guys next Tuesday. Bye now. Thank you, guys. Bye.